In this video, we are going to look at a company that sells widgets. The first part of the video is going to look at this price-demand equation and try to maximize revenue. And then the second part of the video is going to look at both the price-demand equation and then the costs and try to maximize both the revenue and cost to maximize profit. So we have this price-demand equation, and we want to maximize revenue. And the way we do that is we say to ourselves, okay, revenue is equal to quantity times price. We can get rid of quantity here by substituting this equation in, and we get 35,000 minus 5,000 P times P, which is 35,000 P minus 5,000 P squared. So that's our revenue equation. We're trying to maximize revenue, so we're going to take the first derivative, find the critical number, and use the first derivative test to see whether that critical number is a maximum or a minimum. So the first derivative of this function is 35,000 minus 10,000 P, right? We bring the exponent down and reduce it by 1. And so we set this to 0 to find our critical numbers. 35,000 minus 10,000 P, and we get P equals 3.5. I will draw my sign chart for the first derivative. This should be the first derivative of revenue. P is 3.5. And we ask ourselves, is the first derivative positive or negative to the left of 3.5? Well, if we put a big negative number, this term's going to dominate. And we have a minus sign there and a minus sign of the negative number, so we're going to have positive. And then if we put a big positive number in, like still this term dominates and we're going to have negative. So this function, the revenue function, is increasing as the price goes to 3.5 and then decreasing once the price is above 3.5, which means that R of 3.5 is a local maximum. And I'm not going to bother. If we wanted to, we could take 3.5 and we could find out how many units we make by taking 35,000 minus 5,000 times 3.5, and we could find out the revenue by multiplying the units we make times 3.5, and that gives us the revenue. Now, one thing to note here is that we could have done this in terms of X. So if we could have written R in terms of X, so instead of substituting our X out, we could have substituted our P out, then this whole thing would still work and we would end up in exactly the same position. Okay, so for profits, second part, we need to calculate costs. So the cost of production, again, we're going to want it in terms of price, is going to be, well, we have $15,000 in fixed costs plus $1.50 times however many we produce, which is 35,000 minus 5,000, excuse me, minus 5,000 P, which is 15,000 plus 52,500 minus 7,500 P, so 67,500 minus 7,500 P. So profit, a little bit strange, P of P equals 35,000 P minus 5,000 P squared minus costs, 67,500 minus 7,500 P. Don't forget your parentheses. Let's distribute before we take our derivatives. So negative 5,000 p squared plus 42,500 p minus 67,500. All right, so we have our equation for profit in terms of the price set. We want to maximize profit, which means we take the derivative, find critical numbers, draw a sign chart for the derivative, and see whether that's a maximum. So let's take the derivative. P prime of P is equal to negative 10,000 P plus 42,500. We can see when we set that to 0, there's a critical number at P equals $4.25. We draw our sign chart, $4.25. This is the sign chart for the derivative. And we notice we've got a negative term here, so when we put in a big negative number, the derivative of profit is positive, and a big positive number, derivative of profit is negative. The function is increasing, then decreasing, so price of $4.25 maximizes profits. To figure out how many units we make, plug this price into our demand equation. To figure out the profits, we plug this price into our profit equation.